Okay, so for the next day of our wonderful thermodynamics, we are going to talk about the laws. There are 4 laws of thermodynamics, and we are going to go through them one by one. Let's start with the first law of thermodynamics. Okay, the first law, we're going to write an equation down. We're going to explain it that way. It's delta U is equal to Q minus W. All right, so let's talk about what these mean. Q should make sense to you. This is the heat that's coming in. W is the work that is coming out. Now, both of these are going to be in joules. Now, U has a delta in front, so we know what it starts with. It means that it's going to start with a change in, and then the U stands for internal energy. So that's going to be in joules again. So let's think about it this way. So we're going to talk about engines in a wee bit. Let's pretend you have a box of stuff. All right, energy can go into it, energy can come out of it. Now, the heat that goes into it and the work that you get out of it might be equal, and they might not be equal to each other. But if Q is going to be bigger than W, if the heat coming in is more than the work going out, that means the energy of the box is going to increase, right? Which would mean that typically the temperature would go up, okay? If Q is less than W, then the energy is going to decrease. So think about this like your bank account, all right? And your bank account deals with joules, like maybe some freshmen. So the amount of heat that you get in is how much money you make. Money you make. The amount of work that you do is stuff you pay. If you make more than you pay, that's a good thing, and your change in your bank account is going to be positive. If you pay more than you make, that's a bad thing, or maybe you're just the government, then the change in energy is going to be negative. It means you're decreasing the amount of internal energy. Okay? That's the first law of thermodynamics. We're going to apply it to an engine in a second here, but there's one asterisk I want to bring about to you, and that is about this guy here. On your formula sheet says delta U is equal to Q plus W. All right? Now, this is all semantics here, but when you have a plus W, this is talking about the work done on the block, okay, or engine, or whatever you want to call it, okay? So basically what they're saying is if the block here, if this guy does work, that counts as negative work, whereas if you do work on it, it counts as positive, okay? So don't worry too much about the signs. You just got to think about it, and you just got to think, is this energy going into the object, or is the energy coming out of the object? I like to think of the first law in this negative format because it makes more sense as a transaction point of view, but this one, the addition version, is equally valid. It's just semantically different. All right, so let's look at an engine now. All right, so engines in thermodynamics are really boring. They are literally just a box, or a circle if you want to go that way. Now, here's the deal with a heat engine. You are going to have an intake and an outtake. Your input here is going to be Q. We'll call it Q in. What are you going to get out of here? You're going to get out work. Let's put work in black here. An engine, you put heat into it, you get work out of it. All right, this is how a car engine works. Okay, a car engine, you burn the gas to make heat. The heat is what goes into the engine, and the engine is going to turn, you all the cranks and pistons and whatever, and it's going to create work, which is you driving down the road. Now, what's going to happen is the heat going in is not going to equal the work being done. Your car is not that good. So there is going to be a Q that comes out. All right? So there's some things we know from this situation. Something we know is that the amount of energy, what goes in, has to come out of an engine, because let's assume it just runs for yet forever, okay? So your Q in is going to equal your Q out plus W. All right? And there's tons of ways you can rearrange this formula, but what goes in has to equal what comes out in both directions. All right? You could put numbers on this too. So let's pretend that you put in 100 joules of work, and the output, the out heat, is 20 joules. All right? So for our automobile example, this is how much heat is in the exhaust. That's why your exhaust is hot, because it has heat energy that's coming out. How much work do you get? Well, your work is just going to equal 100 minus 20. What's left over? 80 joules of work. That's what you're going to get for this particular engine. Nice. Okay, so what we're going to do now is talk about its efficiency. All right? Efficiency, remember, if you're really efficient, it means you get what you want divided by what you pay. All right? This is the case for everything. This is the case for probability, for, for how many chance, what's your probability of rolling a 6 on the dice. This is also for efficiency. This is for your test score, how much questions you got right divided by how many questions you had to try. Now, for a heat engine, what our efficiency is going to look like is it's what we want. What do we care about? We care about work. This guy right here, this is waste heat, all right, or exhaust. All right, either way, it's not what we care about. We want work. A perfect car will have no exhaust heat. All right, so it's going to be work divided by your Q in. Okay, sound good? Now, your efficiency, which is this stuff, is always going to be less than 1. Now, this is a strictly less than. This is not a less than or equal to. You will have to have some waste heat. All right, this is getting into the second law, and we'll get there in a minute here, but it will be less than 1 every time. It is physically impossible to make it 100% efficient. It's not just impractical, it's the law. Which law? The second law. But we got to talk about something else before we jump to that. We're talking about a refrigerator. A refrigerator works very similar to our heat engine, and in fact, they are drawn remarkably similar to that. Now, let's think about this. When you have a refrigerator, let's think about the one in the kitchen here, you want to take heat out of the middle and pump it to the outside. Now, I don't know about you, but my kitchen is not as cold as the interior of the refrigerator. So we're going to have some heat that goes into the refrigerator, and we're going to have some heat that comes out of the refrigerator. We'll call it Q out. Now, the amount of heat that goes in is coming from the cold side. So we could put, this will be our temperature cold, and this will be our temperature hot. If that helps you think about it, this is the inside of the refrigerator over here. Oh, we should have it in blue. Inside of the refrigerator. Now, to get the heat to go from cold to hot, remember when we talked about heat transfer a while ago, that is not going to happen on its own. What that means is you're going to have to put in work. So work is going to go the opposite way this time. So work is going into the refrigerator to pump heat from the inside to the outside. Okay? This should make sense. This is why your refrigerator has to be, in fact, plugged in to do its job. Okay? Now, this leads us to another fun equation. It's going to be very similar to what it was before. It's going to be slightly modified. Let's see if you can figure it out. What goes in has to equal what comes out. So what goes in is Q in, the amount of heat that goes in. Work also goes in for this one, and that's going to equal Q out. All right? So in this case, what is happening is the heat coming out of the refrigerator is going to equal the heat coming into the refrigerator plus the amount of energy that you're putting in to move it. All right? This is why if you ever put your feet at the bottom of the refrigerator when it's cold, you can feel the warmth coming out of there, right? This is where the heat comes from on your refrigerator, the exhaust port there. Okay, this is where your cat likes to sleep, for example, maybe, because it's nice and warm, because it's not just the heat coming from the inside, it's also that wasted heat from turning the gears, the compressor, and just the plug-in, the P equals IV kind of stuff. Now, refrigerators don't have an efficiency per se. They have something that's very similar to it, though. They have what's called a coefficient of performance. Coefficient of performance. We'll tell you why it's a different letter in a second here. Performance. Okay, but let's just pretend it was efficiency. All right, let's just pretend for now. Now, it's still going to be what we care about divided by what we're paying here. What do we care about here? What matters? Well, what matters is how much heat we're getting out of there, right? So that means that the numerator is going to be the Q out, because we care about, the Q in, because we care about how much heat we're pulling out of the refrigerator. Okay, doesn't matter how much you spit out into the environment there. We care about how much is leaving the refrigerator. You gotta keep those sandwiches cool, right? So it's just Q in. Well, what are we paying? We're paying with our work, just like before. So our coefficient of performance is going to equal the Q in divided by the work. Now, this means that the coefficient of performance can be greater than 1. And by can be, we mean usually. Okay, so it's usually greater than 1, because what it means is, let's just say, for argument's sake, that our coefficient of performance is equal to 3 for this refrigerator that I have right here. Now, if I plug it in and it takes 5 joules of work, what that means is that it's going to be pulling out 15 joules from the inside. So for each joule that I pay, I can move 3 joules. This is like a multiplier, which is why it's called a coefficient. Now, what's going to be your exhaust heat here? How much is coming out? It's going to be 20 joules. Because remember, your exhaust is going to be these two things together. It's going to be the 5 plus the 15. All right. Now, you can have a coefficient of performance that is less than 1. That is not a good scenario. You know, it'd be a very inefficient refrigerator, but it is legal. You know, this could be any number, any positive number. Okay. So those are your two heat engines. Refrigerators are the same, just backwards. We are going to do a lot more with these tomorrow when we talk about cycles, but we need to just have a basics of how it ties into the first law for today. On to number 2, the second law. The second law is something you've actually dealt with a long time ago in chemistry class. Yes, your friend chemistry class. Now, the second law, looks like this. It's delta S is equal to Q over T. Look good? Looks awesome, doesn't it? For this one, we're going to use this a lot less than the first law. So if there's only one you can handle the first law. This is kind of like a completionist sake here. But we do need to understand some of the things, some of the concepts within this. This guy right here, do you remember what it is from good old chemistry? This is entropy. Well, change in entropy, okay. I suppose we should say that. Change in entropy. Before we come back to it, let's talk about these guys. Q is talking about your heat in. Sometimes they put a delta Q, sometimes they don't. Either way, it's fine. Delta T stands for temperature. So now heat in is in joules, temperature is in Kelvin, because of course we're using Kelvin. So your change in entropy is going to be joules per Kelvin. Now let's talk a little bit about entropy before we put this away. Entropy is a measure of disorder in a system. So for example, let's say we're talking about the car, okay? The car is going to take your gas. Your gas is a liquid, and it's going to change it into carbon dioxide, which is a gas. Well, that's a bad example. Your gasoline is going to change into carbon dioxide, which is a gaseous state. Anyways, so a liquid is going to be much more orderly than a gas, because a gas can spread out and get jumbled together in all sorts of which ways. When we're talking about disorder, another way to think about it is how much it can be shuffled. So let's pretend you get a new deck of cards and they're all in order. Ace of spades, two of spades, three of spades, up through king, and then clubs, diamonds, hearts. Then there's only one way you can arrange that. Now, as soon as you shuffle it together, there are many ways you can shuffle it. You could have the two of hearts be first. You could have the 10 of diamonds be first. It does not matter. So there is much more entropy depending on how many ways you jumble them together. If there's only one way, that's very low entropy. If there's a high number of ways, that's a high entropy situation. Now, the thing you gotta keep in mind for entropy is for the universe, entropy is always going to be on the rise, no matter what, guaranteed 100% of the time. You cannot lower the entropy of the world. Now I know what you're saying. You are saying, Mr. Keeney, I can rearrange that deck of cards and put it back in order. And I totally agree with you, but that is a localized reduction in entropy. If you go through that amount of work to rearrange the cards, what you are going to be doing is spending a bunch of time moving your arms around, and your arms will do basically the same reaction as this guy, just with sugar and changing it to carbon dioxide as you have that habit of breathing. Now, that carbon dioxide will get all jumbled around. All right? So as you lower the entropy of straightening out that deck of cards, you raise the entropy of changing those sugars in your body to carbon dioxide. Now, the amount that this rises is going to far outweigh the amount that this decreases. So as a whole, the amount of entropy is going to go up. Now, this will happen for every single thing, unless, of course, you get the temperature to a very, very low, being 0, because of the third law. The third law says at 0 Kelvin, negative 273.15 degrees Celsius, a crystal has 0 entropy. Now, why is that the case? The reason why is because the atoms will actually stop their motion, okay? The atoms will stop moving and they'll hold perfectly still. So there's only one situation that can tie them all together. Now, there is an asterisk here, and you cannot get to 0 degrees Kelvin, 0 Kelvin. Now, Mr. Keeney, that's a pretty strong assumption here. Yeah, I know. But let's think about it. If you have your drink at room temperature, how do you get it colder? You put some ice in it. Why does it get colder when you put ice in it? It gets colder because the heat is going to go from the drink to the ice because the ice is at a lower temperature. If you want to get something to 0 degrees Kelvin, you have to put something next to it that's below 0 degrees Kelvin. Now, if 0 degrees you can't get to, you ain't going to get to a negative Kelvin because that's below something called absolute zero. Therefore, that there is entropy 0 at 0 Kelvin, but you're never going to get there. Okay? So there is a cute saying that some people like to help you remember this types of things here. First law tells you there is a game. Now that means you can change heat into work and work into heat. Nice. The second law tells you is you will lose if the temperature is more than 0 degrees Kelvin. Now, the reason why you'll lose is because entropy will always bleed off some of your energy here. Now, your third law tells you, generally speaking, you cannot have 0 degrees Kelvin. So, you cannot generate 100% efficient anything because you are always going to lose some energy through entropy. Okay? And you cannot get to 0 where that wouldn't happen. So those are your 3 laws. Now, Mr. Keeney, you promised me 4. I agree with you 100%. Let's go to the final law, which is the 0th law. There is no 4th law of thermodynamics. Now, why is it the 0th law? Because this came after. But why don't they just call it 4th law? But it is a prerequisite, though. Whatever. So it came after, but it's a prerequisite to the first 3 laws. So they just left it this way. Now, what they say is that if state A is at equilibrium, we'll use a triple equal sign for equilibrium, thermal equilibrium, okay? So that means heat transfers back and forth is equal. They're at the same temperature, really. State A is in equilibrium with state B, and state B is at equilibrium with state C, then, do you know? State A is going to be at equilibrium with state C. Yes, why yes, it is the transitive property for thermodynamics. And that is what the 0th law says. I don't think you need to devote a lot to understand this one. It's just something that's out there. And yes, it is real. You can look it up. I promise. All right. Hey, there isn't really a lot of math for this one. I mean, there's the heat engine calculations that we went through, but that's about it. The real fun is going to start tomorrow with the cycles, but we'll see you then. Like and subscribe.